Okay, hey, here, welcome to week number 2. As I told you in the email I sent last night, I hope you've gotten started with the chapter 24 in Survey or chapter 6 in the OpenStax, and it's Gauss's law. And so hopefully you're working towards that. And then I told you Monday morning, so here we are, Monday morning, I would work on our second remote lab. And so here I am. And so whenever you get a chance to start this one, just remember it's due Sunday night. And hopefully also today I'll get over to the Canvas and unlock it so you'll be able to turn it in, because I know some of you will want to turn it in right away. Some of you will probably do this today on Monday when you get it this afternoon. But to get us started, go to your lab manual. Remember that lab manual was in the email I passed out or sent out on the first week. And I've opened up the lab manual to page 4. I got the hard copy. You can do that or the PDF. But the lab is the second one in the book. It's called the inverse square law of electricity. And we want to see how that works, or what that is. So give me a few minutes to kind of set up a lecture, and then I'll use the board here to set up the table, and that's what you're going to need to do. So I'm going to come over to here and then just hopefully remind you of something you learned in the first chapter. And that was this, that if you had a point charge, let me just call it Q, there would be an electric field from it. Let me grab the blue marker over here. And so if I were to try to draw it so that it kind of helped me visualize, I would do something like this. And the equation we learned, of course we called this Coulomb's law, was that out some distance, and so I'll just put a little X right here, and say if you were a distance R away from that charge, the value, the magnitude of the electric field, and so I'll just do a little arrowhead, excuse me, a little arrowhead there, and we learned that the value of the electric field was Coulomb's constant times that charge over R squared. And that was for a point. What you will see as you start to do Gauss's law is, even if you don't have a point, as long as it is a spherical object and uniformly distributed, that is, the charge can be on the surface evenly spread out, or the charge could be distributed inside, and of course if it's inside, then we have to have an insulator. Hopefully you caught that too, right? All the charges go to the surface for a conductor. And another thing we learned in chapter 23 is that the distribution of the charge on the surface of a conductor is related to the curvature of it, the radius of curvature. So for a sphere that is a conductor, it would all go to the outside. So let me go ahead and get rid of this. And it would also be evenly distributed. And so this is what our equipment is going to look like. Our equipment today is not really a point, it's really more of a sphere, and it's a conducting sphere. Watch, I'll come over here back to the table. This is it. This is the object we will be using here today in the lab. This is our ball, if you will. It's a sphere. It's a conducting metal sphere. And when I charge it up, and that's what the equipment here is for, and I'll show you the equipment in just a second, the charge will build up and it will be uniformly distributed. And what you're about to learn, and maybe you already have by the time you see this video lab, but in Gauss's law, we show that even though this is not a point, it still creates an electric field. And if you measure from the center of the sphere, and so you come out some distance here, and so let's call that distance r. The value of the electric field still comes out to be Coulomb's constant times the charge over r squared. And that's kind of interesting. And in fact, it's so obvious, or maybe not, I shouldn't say it's so obvious, but it's such a same equation that I think sometimes students kind of miss that. They don't realize we're doing something different. And I want to emphasize we are. We, like I said in the video lecture and in the textbook, will prove that if you have a metal conductor, the charges will be on the surface, they will be evenly distributed, and the equation for the electric field, or the function of the electric field, has the same as if all of this charge was at the center of the sphere and was a point. And so that becomes kind of interesting and useful. So today's lab is this. Today's lab is, let's go ahead and actually measure the electric field. I mean, according to the math, according to the theory, is that it will behave just like a point. And a point would behave just like this. And so this will give us a chance to actually measure the field. We'll see if, first of all, if Coulomb's law is right, and then second of all, see if applying Gauss's law to a sphere, which gives us the same equation as Coulomb's law, is actually right. So we're gonna give it a try. And of course, in this remote setting, I'm going to be collecting the data for you, and then you're going to analyze the data here. All right, so let me come over here to the middle whiteboard here, because this really is the basics of the lab. I'm going to, and I guess I'll say working with you, we'll measure the value of the electric field at different points from the center of this sphere. Then in a second I will show you the equipment, and you'll see as I show you the equipment, the closest you can really get if we measure distance in meters is about 10 centimeters, 0.10 meters. So that'll make our first measurement. And then as we read the instructions, you'll see it says move a centimeter at a time maybe I'll give myself a little space. You'll see why here. Okay, so here's R and here's E. Let me move R up a little bit. There's the M. So what was that? 18, 19, and then 20. And then it says, okay, well, once you get to 20, it changes a little quicker. So let's go by fours. And so this is 24, 28, 32, 36, 40, 44, 44, 48, 52, and then give myself a little bit of space here. And so here's R, here's M, and we're just going to go to 60 centimeters away. So another 4 would be 56, and then finally 60. So that'll be our last measurement. And maybe to make the table a little more complete, note that the electric field is measured in newtons per coulomb, so newtons per coulomb and newtons per coulomb, and we're going to create a pretty small electric field, as you'll see. It's actually one of the challenging things about this lab is we want to make the field, big enough that we can measure it, but small enough that it's safe. And so we're going to be touching some charges here. And so you'll see that the fields are pretty small, but definitely measurable here. Okay, but then you're asked to do this 3 times. And so that's why I wanted to leave a little space here. Because each time we do it, we're going to put a smaller and smaller and smaller amount of charge on it. So the last time we do it, we will put a charge. Why don't we just call it Q? Because this will be twice Q. And the first time we do it, we'll do it with the most charge, and that's 3Q. Let me come back over here to the equation. Here is the whole purpose then, and I'll say it again. We want to see if this equation is valid. See, and what this equation is saying here is that the electric field should decrease according to 1 over r squared. That's why the title of this lab is the inverse square law of electricity. And so that's what this table will be doing. But you'll also see in this equation that the electric field is proportional to the charge. And so that's why we're going to do it 3 times and have 3 different charges, so we could also see if it is proportional to the charge. So we will hopefully see both effects here, that the electric field is an inverse square law, but it is also proportional to the charge. And I know that proportional to the charge isn't in the title, but it's still important and good to see here. So let me go ahead and kind of finish up my table here on the board and take this as an opportunity for you kind of to decide how you want to record down your data. You can do it as simply as I am and write it out old school, pencil and paper, although that's probably not a good choice, because we do want to plot this. And so you guys all learned graphical analysis in Physics 121, and so maybe that's the easiest thing to say, is to go to your virtual desktop that the school provides you through Pipeline and make yourself, by default you'll have 2 columns, and make yourself 2 new columns and make these plots and graphical analysis. But some of you maybe even prefer or already know how to do Google Sheets, and so if you want to use Google Sheets and do a spreadsheet, that's fine too. Or Microsoft Excel, or really any program. Is the old Lotus 123 even around anymore? But whatever spreadsheet you want to use or program you want to use, we can make a graph. I just know that we as a school supply you with a virtual desktop and graphical analysis. And graphical analysis is so both simple, which also makes it user friendly. It's kind of really nice to work with. But then again, those other ones are so universal now, Google Sheets and Microsoft Excel. They're way more powerful, which makes them a little bit less user friendly. So whatever you want to do. But we're going to plot this before the day's over. And so that's what you'll ultimately be turning in, is these tables and the graphs representing the data we're about to collect. So that's what you need to do this week and turn in Sunday night, okay? All right, so I think you got the idea of the lab, and now I think we're actually ready to begin. And I would say for you guys, if your spreadsheet isn't up and running, maybe you want to pause this video and make two windows, one of this me doing the lab and another one with the Excel spreadsheet, so that you can start filling it in, or the Google Sheets, or the graphical analysis. All right, so here we go. Let's look at the equipment here. And so here I have set up the equipment, and as I pointed out earlier, this is that big ball that we're going to charge up, and it gets charged with this little device. This device is kind of plugged into the wall, and I'll kind of point it to you, but you can see that there's three little jacks for me to plug this in, and I can charge it. This is the biggest one, so I'll plug it in there first, and then so that's 3 times. I'm holding it upside down really, but there's a 3,000, a 2,000, and a 1,000. So we're going to have our charges, and they're going to be factors of 1, 2, and 3. And so once the charge gets on here, it will make this electric field. And this little metal thing hooked to this little probe here is our fancy equipment that, of course, is why we have to have these video labs, because you don't have this kind of thing in your house, and they're a bit pricey, so this is just how we have to do it remotely. Okay, so I'll just kind of look down on the scale, and I'll say the number and write it here, and so that's how we'll be working here, right? We're a team. You're collecting data, and you're going to do the graphs and whatnot, and answer the questions. And when I think about it, I don't think there are discussion questions on this one. So a little bit easier than last time. And we'll just take our measurements. All right, so I'll begin by saying that if you remember from last week, we just want to make sure we kind of zero everything. And so, as you know, if I touch this big ball, this should discharge it. It should come on me. I'm even going to do one more thing. You can't really see, but I took this wire and I actually plugged it into the ground down there. And so if I touch it and then touch this, then it literally is grounding. And so that should take all the charge off of the ball and off of me and onto there. And so they'll come over to my meter and check to see if it's reading 0. It is. I even have a button that I can reset it to 0, so that's good. I actually have my probe already set up at the first reading right here, 10 centimeters away. Maybe I'll get my marker opened up and ready to go. And since there's not much charge here, I want to be a little careful with my feet and touching and shuffling things around. Because when two things rub, it doesn't take much charge. And so really the charge on this ball really isn't any more than I would get if I just kind of rubbed my hands on the desk. And so I discharged the desk with some water. I just kind of wiped it down with water and all the other equipment here. And so let's begin here. All right, so trying not to shuffle my feet too much, I'm going to jump over to the full charge. And I'm going to try to keep my body away from it, because again, charges on my body. And it looks like I am at about 49. No, 49. So I'll go ahead and say, here's my first reading, 49. And the charges do tend to leak off with the moisture in the air, so I'm going to go as quickly as I possibly can. And this is going to be then a 44. And then I will go to 12 centimeters and get a 39. And then I will go to 13 centimeters and I will get about a 30, let's call it 36. And then I will go to 14 centimeters. 30, should I call that a 3 or a 4? It's an analog dial. I'm going to call it a 34. Call that a 31. call that an even 30. Let's go with 29. Now, the scale's kind of nice. I'll go one more here and then I'll show you something here. Let's call that a 20. Oh, maybe I'll call it a 28. But when we start to get under 30, you can change it to a scale that can read things from 0 up to 30. And so the other one I had it on was 0 to 100, and it's getting kind of hard to read the details. So I'm going to switch it over here. And I can see things a little bit better. Okay, and so that's really a 28.5. Okay. So let me go to 19, which would be a 20. Oh, I'm sorry. 1, 2, 3, 4, 5. I read that wrong. That's a 28.0. Okay. Let me read this one then. So this would be 2, 4, 6, 7. So this is a 27. 26. And now, so we can go a little faster and cover some distance. Let me go out 4. Let's see, that's a 22, 23. 28. 20. Ooh, it's not quite a 21, but it's not really a 20. Maybe I'll call it 20.5. 32. Looks like that's about a 19. Is that true? 20, let's see, that'd be 18, 19. Could be about a 19 and a half even. So where was it? 36. Yeah, let me call that an 18 and a half. And so 18, 16, let's call that a 17 and a half. Well, no, I'm going to go with 18 even on that one. 18. Let's go to 44 here. 16, 17, 5 really. 4 more make 50. Call it a 16 and a half, or should, well, let's see. I can see it a little better. Yeah, that's pretty much in the middle. Let's call it a 17. And then 50. Oh, that's where I messed up. Went a little too far. Yeah, okay. Definitely 17. Okay, so 52. I'm still going to call that a 17. And a 56. I'm still going to call that a 17. It's getting closer to about 16 and a half. But one more. Yeah, I'm going to call that a 16 and a half. All right, so it's barely going down, but that makes sense. I kind of, think that's following a good pattern. And so let's keep collecting data here, but eventually you're going to plot that, and hopefully this will follow the pattern, or I should even say roughly follow the pattern, because this is really hard to get anything of quality with these small but safe fields that we have. All right, so let me come back here and put it at the 10 to kind of get us started, and just to kind of start everything anew. I'm going to go ahead, and see it's a little bit off by the time I finish the whole experiment, but not quite at 0 anymore. And that's common. If you guys were in class, you'd probably do this a couple times, and I'd say just take the best data you got, because it's just real finicky, and especially in a class with everybody walking around each other. That's maybe the good thing about today's lab, is we don't have other people next to me here, and things shuffling around and computers on and all that. All right, so let's run this then a second time. And this time we're going to charge up that ball, but with a smaller amount. So if last time was 3Q, we're going to call this 2Q. All right, so here I go, and hopefully not too much shuffling, but also kind of on the fast side. Let me move it over, and let's see what I initially get. And it looks like I'm at about a 30, I'll call it 32. Okay, and then I will move it to an 11, 20, and we'll call it a 28. We'll move it to a 12, and I'll call it a 24. And then I'll move it to a 13, and I'll call it a 21. And then I'll move it to a 14. Oh, and I should pause, because remember I said anything under 30, I can read a little better if I go to the next scale. So I'm already under 30 by quite a bit. So let me go to the next scale. Okay. And I can read a little better. That looks like a hair over 18, but not quite to the 19. So let's call it 18.5. Let's call that a 2, 4, 6. That'd be a 16. That's really good. 17 right there. 17. Let's go to 16 here. And that's a hair under 16. I wouldn't quite call it a 15 yet. So how about a 15.5? Should I call that a 14? Oh yeah, I'll call it a 14. Why not? Yeah, let's call it a 14. What am I at? 18. Okay, so yeah, so then that's, oh, good. So that'd be 12, 13 and a half. Okay, so 13 and a half. And then let's go to 19 here. I'll call that a 12 and a half. 12 and a half. Or is it a 13? No, I'm gonna go 12 and a half. Okay, then at 20 here, this would be a 12. Yeah, good, 12. Okay, then I'll go to the 24. Okay, and that's, 9.5. No, let's call it closer to 10. Okay, so let's call that a 10. And so if I go to 28 here. And then also, anything under a 10 gets kind of hard to read on this scale, so I could switch it, and I'm now under 10. Let me go ahead and switch it to the next setting. All right. Oh, good. And so that's really an 8 there. So let me go to 32, right? I'm at 30, 32, okay. And that's, let's see, not quite a 7, but more than 6.5, because they have a mark there for the 6.5 on this low scale. So let's call it, not 7, 6, let's call it 6.75, now that we've got a little more fine-grained scale. Let's go to 36, and that seems to be dead on 6.0. Now let's go to the 40. And the 40 seems to be, let's see, that would be 5.5. I'll call it a 5.6. So 5.6. Let me just check that one. 5. Oh yeah, it's so small. It's kind of varying with just me standing here, because that's probably a 5.7 and jumping around there. So as we get to the end, we may not even want to have this as part of our curve fit. We'll see if it's any good. But that's a 5.5 there. 48, and so this is the part of the data that is unreliable. So if things look funny on our graphs, we're going to kind of just ignore this part. But that's an even 5. Oh yeah, and wow. Okay, let's call it an even 5 again. 52. Maybe if I come from this side. 56. Let's call that a 4.75. And our last one, and hopefully somewhat reasonable one, it would be about a 4.6. All right, it's good. And again, you can see that it got hard here at the end. They get small, and you can see now why I always recommend, and I did it too, the big one first. The big one's the most charge is the easiest one to do, and the one that gives us the best results. But we want to see if it changes with different charges. So now on to the hardest one, a very, very small amount of charge. And so let me reset it. And so I'm going to come back over here to be 10 centimeters away. And what did we start on? See, last time we only went up to 32. I'm going to take a risk. I'm not even going to put it on the big scale. I'm going to just put it on the scale that reads to a maximum of 30. And see what I get. I'm going to kind of discharge the ball here and reset to 0. Okay. And I'll do this last and hardest one. Try to be real careful here. And let's see if it stays under 30, which I think it will. Yep, sure enough. Not even close. We're looking at starting at a value of about 15. okay? And actually, this is really good. I mean, I'm going to plot this, but can you see this is about multiples of 3. 15, you double it, 30, you triple it, you get about 45. And so we're a little higher here. Actually, almost be perfect if this was a 16, right? But it's not. It's a 15. All right. And so let me move this to here. And so that looks like it drops to about a 12. Let me move it to here. That's a little more than 10. And not quite the 11. It's kind of in the middle of that, those two little tick marks. So I'm going to call it 10 and a half. 13, I'm going to call that a 9 and a half. Let's go to the 14. Oh, that looks like about a dead even 8. Wait, that's a pretty good drop. I'm going to go back to the 13. Did I read it wrong? Yeah, no, 9 and a half. Yeah, this was probably a little closer. Now, like I said, this one's going to look the best we can. This one's really hard to get anything of significance. It's just a small value. All right, I'll keep going, and I'll go to 15. And usually this is the one also I should point out. I tell the students, try to get out to 60, but good luck. We're just going to go as far as we can, and then if it looks terrible, we'll stop. Okay, so let's see, what scale am I on? The 30. So that would be about a 7-ish. Oh, and I'm under 10 by now, so let me go ahead and switch to a little more granulated scale here.